Hello, in this video we're going to solve some problems using linear algebra and matrices. These will be some engineering and other science problems. In our first example here we've got some kind of a steel beam, and the beam is cut across, so we're looking at a cross section here. We've got the outside perimeter or the outside edge of the beam, and the temperatures are measured on nodes, these points here on the outside edges, and then we've got four inside nodes. And although we can't stick a thermometer inside the metal beam, we know through some sort of empirical testing or some sort of experimenting and research that the temperature of any one node is equal to the sum of the four closest nodes on the horizontal and vertical axes divided by 4. And so we can solve for T1 this way, and then we can put these into simultaneous equations. We're going to have four different variables, T1, 2, 3, and 4, and we want to put that in a matrix form so we can solve the system of equations. And so in a matrix we're going to have spots for T1, 2, 3, and 4, and then what we want to do is have the coefficients of those in each of these spots here. And so they've given us our first equation, 4T1 minus T2, and then there's nothing in the T3 spot there because T3 is not adjacent on the horizontal vertical axis to T1, and then minus 1 for T4, and all of that is equal to the sum of these two outside temperatures, which is 30. And so we're just going to put again the coefficients for each of the other three nodes on the interior. And in order to solve this problem, what we want to do is transform this matrix so that we can get the identity matrix. So we're going to do some row reduction. We're going to multiply and divide by scalars, and then we're going to switch rows and or interchange rows and do some addition and subtraction with rows. And when we multiply a row by a scalar, then we want to multiply all of the elements in that row by that scalar. When we add and subtract rows, again, we need to add and subtract all of the elements of each row to and from each of the others. It's given us our first move here, our first transformation. We're going to interchange rows 1 and 4. And so when you look at this, if you're looking to make the identity matrix, you might first think, well, I should just take this diagonals. We've already got 4, 4, 4, 4 there. What we want is 1, 1, 1, 1 across the diagonal there, starting at the top left, moving to the bottom right. And we want all zeros in the other spots. And so you might mistakenly think that we should start by trying to get all ones, that you wouldn't actually interchange these two rows. But in doing so, there's a high chance of making mistakes, or at least coming up having to deal with really clunky, inconvenient fractions with large denominators, and making it difficult, or at least time consuming, to do row addition and subtraction with a number of different denominators where there aren't simple least or lowest common multiples and such. And so this process takes quite a long time, and it requires that we have a lot of patience, and also that we don't make any mistakes in the arithmetic in each of these row operations here, because if we make even one mistake along the way, we're going to come up with nonsensical errors. Okay, so first we're going to add to row 4, 4 times row 1, because we've got a 4 in this spot, we're looking to get a 0 in that spot. And then we're going to subtract from row 2, row 1, again, because we've got a negative 1 here, we're looking to get a 0 there. And so in the identity matrix, we have 1s on the diagonal starting at the upper left, going down to the bottom right, and nothing but zeros underneath each one. And so in the first row, the first column will have a 1, and all of the other columns will have a 0. In the second row, the second column will have a 1, and all the other columns will have a 0. In the third row, the third column will have a 1, and all the other columns 0. In the fourth row, the first three columns will be 0, and the fourth column will be 1. And that'll give us, so we've got T1, the first column is our T1 values, the second column is T2, third column is T3, fourth column is T4. We've got 4 different variables. And then on the other side of this line, I just put that there to make it easier for me to understand that that's our equal sign. On the other side of that, we're going to get what that equals. The sum of all of our variables, coefficients times the variables, is equal to these numbers. And so when we get that identity matrix, the numbers on these side are going to be equal to the values of our variables. And so we want to get a 1 here. We're going to multiply that first row by -1. And then we want to get a 1 here, so we're going to multiply that by 1/4 and divide it by 4. And again, this takes quite a long time. And so that's why technology has really become very useful. Guys like Gauss and Jordan and other mathematicians came up with these techniques, and they are very useful. We can solve these simultaneous equations, which come up in business, logistics, and a lot of different sciences. Here we have a heat transfer problem or an engineering problem. But a 4x4 matrix for our variables is really quite small. We could be dealing with hundreds and hundreds of rows and columns, especially when getting into economics and especially international trade. And so technology is really indispensable. And so being able to do these row operations is important, but more importantly, we should be able to understand when we need to find the row reduced echelon form and what these techniques are used for. When I was first exposed to linear algebra, I was an undergraduate in one of my calculus classes we had. I think it was Calculus 3, and then there was a linear algebra supplement in the middle there. And I remember this being a rather awkward process, especially, again, in this problem, the first response would be to try to make this the identity matrix without interchanging those rows. And like I said, if they didn't give us that hint there to interchange rows 1 and 4, we could easily come up with these ridiculous denominators and fractions and mixed fractions, trying to get nothing but zeros and ones in all the spot with a number of fractions really becomes quite an obtuse process and could take hundreds of steps really, depending on the size of the matrix. And so I like to rely on technology just like most engineers and scientists. Of course, it's just more productive, it's more efficient. Nobody wants to spend 10-15 minutes doing something that could take seconds for a computer to do. But as a math student, of course, if you just submit the answers on your homework, then you're not likely to get any credit. You're certainly not going to get full credit. And then on tests, usually you don't have access to all of your calculator or computer technologies. And so there's kind of a disconnect between the real world and education. And it's for a reason that we want students to be able to do these things. But of course, math teachers have to be aware that the removal of technology from the classroom also turns a lot of students off from these disciplines which they find impractical. I mean, it's not like you're walking down the street and you need to solve a matrix. I mean, certainly not in mathematical terms. Maybe some of you have seen the movie Matrix and you can identify with some of the topics there, but it's not exactly what we're dealing with here. And so in this step, I'm going to just combine several steps because this is becoming rather long. And so we're going to divide our row 4 by 12 because we want to get rid of that 12. We want to have a 1 there. And then we're going to add 2 times that new row 4 to row 3 because we want to get rid of that 2. Then we're going to divide row 3 by 4 because we want to make that 4 into a 1. And then we're going to add row 4. This will be a 1 down here in the lower right. We're going to add that to row 2 to get rid of that 1. And we're going to be left with nothing but the identity matrix except for our first row here, which we can deal with in the last step. And so in our next couple of problems, we're going to use technology to do the row reduced echelon form to find the identity matrix, because again, it takes seconds only to do what it would take a human to 10-15 minutes to do. And technology is not only faster, but it's more reliable. It's not going to make those dumb errors that most of us have made on tests, just what you want to call it, a brain fart or whatever. But a lot of us make just silly errors that result in erroneous answers. And those are the things that the technology won't do. So we're going to subtract R3 from R1 to get rid of that 1 there, and then we're going to add 4 times row 4 to this row 1 to get rid of that 4. And so here we have the identity matrix then. Again, the first row, first column has a 1, and then nothing else in the first row other than zeros. There are no values, no non-zero values to the right of each non-zero value in each column, or sorry, in each row. And in the identity matrix, there's only one non-zero value in each row, and the column of that non-zero value is the same as the row of that non-zero value. And so here are our values for the T1, T2, T3, and T4. And so if we wanted to write that out, we got T1 equals 20 degrees, T2 is 27.5 degrees, T3 is 30 degrees, and T4 is 22.5 degrees. All right, so that took about 10 minutes to do. And it's more convenient than before some mathematicians a long time ago spent years and years and years developing matrices. It's certainly more convenient to work with than techniques that were predating these matrices in row-reduced echelon form, but it does take quite a long time. And so now, since we have high-powered computing technology, that's certainly the most efficient way to do things. In our next example, we've got to do a little bit by hand, and then we can leave the heavy lifting, the legwork, to the computer. I suppose we could find an online calculator for the center of mass that we could just plug in these values in. It's going to come up with the center of mass, but again, we should know something about the math and physics that we're working with here. We're looking for the center of gravity of this triangular plate. It's of uniform density and thickness. The vertices are labeled on the xy axis here, and we can put those into I and j components of a vector. We've got 3 1-gram point masses at each of the vertices, here, here, and here. And so with those point masses, then our center of gravity is equal to, or also could be called the center of mass, is equal to 1 over the mass times the first point mass times the first vector in ij components, and then just sum all of those point masses and the ij components up to the end. So for example, Cg in this case is equal to 1 over 3, because it's 1 over 3 grams, and then we're going to multiply that by 1 gram times, again, we're going to split up our vertices into I and j components. 1 times 0, 1. Remember, the top value is the x or the I, and then the bottom value is the y or the j. 2, 4, and then we're going to add to that 1 times 8, 1. And these here are just scalars, so 1 times any vector is just the vector itself. Scalar times any vector is just the scalar times each component of the vector. We're working in 2 dimensions, so we've only got I and j components. And so we can get rid of those 1s, those aren't important. That's just the identity vector. And so we're just going to add these together and divide it by 3. 0 plus 2 plus 8 is 10. 10 divided by 3 is 10/3. 1 plus 4 plus 1 is 6. 6 divided by 3 is 2. And so those are our I and j components, and then we can put that into x and y coordinates by saying 10/3 and 2 is our center of gravity. 10/3 is 3 1/3, so we're looking at right around here, and 2, and so we can see that's the center of the triangle, center of mass of the triangle. That's fairly intuitive. In part B, determine how to distribute an additional 6 grams at the 3 vertices. So we're going to put an additional 6 grams, W1, 2, and 3, such that the new center of gravity or center of mass is going to be at 2, 2, so we're going to shift that over to the left by 1 1/3. And we don't know what W1, W2, and W3 are, but we know the sum of those is equal to 6. We're going to put a little bit here, a little bit here, and a little bit here in order to get that new center of gravity. And so again, we're just going to use that same equation, center of gravity or center of mass is equal to 1 over m, or 1 over, now our mass is 9 because we're adding 6. And we're going to multiply that by, remember we had 1 up here before, so we're just going to say W1 plus 1, and multiply that by the I and j components there, plus W2 plus 1 times 2, 4, plus W3 plus 1 times 8, 1, and all of that is equal to our new center of mass, which is 2, 2. And so we can multiply by the scalar 9 to get rid of 1/9 over here, and then we're going to distribute the 1 and the w out to our vectors. So we're going to get W1, 0, 1, plus, again, the scalar 1 times any vector is just 0, 1, plus W2, 2, 4, plus 2, 4, plus W3, 8, 1, plus 8, 1, and that is equal to, we're going to multiply by 9, so that 9 cancels out the 1/9 over here. 9, that's a scalar. 9 times 2 is 18, and 9 times 2 is 18. And now we want to take these values. We don't have any variables attached to these values here, so we're going to subtract those over to the other side. This is just vector to minus vector, so we've got the I component of this vector minus the I components of each of these 3 vectors. We're going to isolate our variables over to one side and our known constants over to the other. So we've got W1 times 0, 1 plus W2 times 2, 4 plus W3 times 8, 1, and that's equal to 18 minus 8 minus 2 minus 0, or 18 minus 10, which is 8, and 18 minus 1 minus 4 minus 1, or 18 minus 6, which is 12. And now we've got something to work with that we can put into matrix form. So we've got 3 variables, W1, 2, and 3. Our coefficients of those 3 variables is 1, 1, and 1. And then we know the sum of all 3 of those is 6, and we're just going to take our I components across the top there, 0, 2, 8, 8, and our j components, 1, 4, 1, 12, and we're going to take that matrix, put it into row reduced echelon form, and that's going to give us our solution for W1, 2, and 3. Slowly. And there we are. So it took me less than a minute just to enter these values. I've got GeoGebra here in the spreadsheet form, right? And so I entered the values into the spreadsheet there, and then typed in reduced row, and it even completed the function for me. And then just entered M1 into that box there, and it churned out our row reduced echelon form there, our identity matrix, in a matter of milliseconds. We got W1 is equal to 3.5. Remember, our units are grams. W2 is equal to 0.5 grams. W3 is equal to 2 grams. And so, even though this was a 3 by 3 matrix, it did solve the problem quite a bit faster than we would have been able to do by hand. Again, technology increases our efficiency and productivity, and that's why in the working world, with automation becoming the standard, then we're working with more and more technology. We still need to know when and where to use these matrices and how to solve for these variables, but the easy part is just the arithmetic, and that's the part where we would be most likely to make mistakes. And so we can just let the technology do that for us. In the classroom, well, hopefully over time teachers will start integrating more technology into tests. I've had a few teachers along, even in math, who allow for open book and open resource testing. Of course, then the problems become slightly more difficult or more complex, but it's more realistic that students would be able to use some resources, and it also makes things a little more interesting for the students. So we've got a roundabout here in England, and we've got these nodes or these intersections A, B, C, D, E, F. I'm going to label those A, B, C, D, E, and F. And at those intersections we've got traffic in and traffic out. And so at A we can see incoming we've got X6, and then we've also got an additional 60 coming in, and then outwardly we've got X1 going out from A. In B we've got X1 only coming in, and then out we've got 70 and X2. For C we've got X2 and 100 coming in, and then coming out is X3. For D we've got X3 coming in, and going out is 90 and X4. For E coming in is 80 and X4, and going out is X5. And then for E, we've got, or sorry, for F, we've got X5 coming in, and going out is X6 and 80. And so we want to put this into matrix form again. And so again, on the top we've got several different variables in X. And then we've got these intersections here. This isn't yet a matrix, but you're going to see the makings of a matrix here in a moment. So we've got X values of 1, 2, 3, 4, 5, and 6. And then we've got some number of cars on this side here. And so at A we've got 1x1, and then that's minus x6. We've got zeros along the rest. We want to get a positive value along the diagonal here, positive values for our x1, x2, x3, x4, x5, just so that we can make the arithmetic a little easier. And so then to get positive x1, we're going to subtract x6, and we got 60 on that side left over. And for the next one, we've got positive x1, and we're going to subtract from that x2. We move the x2 over to this side, and we get 70 left over. And then for letter C, we don't have x1 anymore. We've got positive x2. Again, we want to keep it positive. We're going to subtract from that x3. And we don't have any of the other x values. And then we've got to subtract that 100 over to the other side, so we'll get negative 100 there. And then for D, we've got, we'll stay with the positives on the x1 through 6. We'll subtract the x4, so we got minus 1, again 0, 0. And we're left with 90 on that side there. For E, we're going to have zeros up to x4, which will be 1. We'll subtract x5 from that. And then we'll have to move that 80 over to the other side, so we'll get negative 80. And finally, for F, 1, negative 1, and 80. And so you can see a matrix in here, right? Quite easy to see a matrix right there. And so in order to solve for these x values, we're going to put it in GeoGebra and look for the row reduced echelon form. And in this type of situation where we've got six x values, and you can see only ones and zeros and negative ones in each of the rows anyway, we're going to come up with what's called a free variable. And that free variable is going to be sort of the basis for our solutions here. So we've done the reduced row echelon form, and what we end up with is x1. So we've got 1s along the diagonal here. So we get, first of all, x6, our bottom value here is all zeros, and so x6 is what's called free. And then all of the other variables are defined in terms of x6. And so if we can find out what is x6, we can just find out, and that's the first bit of traffic going into our first intersection there. It's not coincidental that x6 is the component of traffic in the roundabout at what they're calling our first intersection. If we can find out what that is, we can measure that. Sometimes they put little tubes or sensors over the road in order to figure out what the average is over time. And so we can get x1 is equal to, we're just going to move this -1 over to on the other side. We get 60 plus x6. x2 is equal to x6 minus 10. x3 is equal to this one here, 90 minus, or sorry, 90, x6 plus 90. x4 is equal to x6, and x5 is equal to 80 plus x6, or x6 plus 80. Either way, we got commutative property of addition. And so, again, x being free means we need to know that variable in order to solve for all of the other variables. But that should be easy enough to measure, given that this is a real-world example involving traffic, which is tangible and it's dynamic, but we can measure averages over time. And so you should be starting to see where we can use matrices, and especially technologies with matrices, to solve real-world engineering and physics and other science problems. And so once again, we see that math is most certainly in every aspect of our life. And while it's important to be able to do these calculations by hand, it is also becoming more important that we know how to use technology, which means that we don't have the possibility or the likelihood of data loss or error that we would have otherwise if we were doing it by hand, but we need to know which techniques to use at what times in order to come up with reasonably meaningful solutions. Okay, thank you.